In section 1.7, we'll be talking about inequalities. Okay. Now, inequalities we solve very similarly with equations. But there's three main differences. One of them is that we reverse the inequality if you multiply or divide across by a negative. And the reason why this is because on a number line, this is 0, and this is 2, this is negative 2. Now 2 is bigger than 1, right? But if you look at the negative sides, the larger the actual number is, the smaller that value is. So if you multiply by negative 1, you can't keep that inequality because looking at your number line, the bigger numbers are this way, right? So we get bigger as we go to the right. So the reason for that is whenever you multiply or divide across the inequality here by a negative number, so if we multiply by negative 1 or divide by negative 1, we switch the inequality. That's why we do that. Also, the difference between an equation is there's usually more than one answer. If the answer is x is greater than 2, well, on a number line, that means if this is 0, here's 2. Any number greater than 2 would be an answer. 2 actually wouldn't work. We'll talk about that in this third difference. That if you see one of these symbols, this means exclusive, meaning not including. And if you see one of these symbols, this means inclusive. When you're graphing exclusives, you generally have an open circle on that number, meaning up to 2, but not including 2, whereas inclusive would have a closed circle. In this section, we're also going to be talking about interval notation. And with interval notation, we would actually write the answer for this as open parentheses, which is what we use for exclusive, 2. So you start from the left side of the answer, that's the 2, and then you talk about the right side of the answer. So the right side would be infinity, and we close that with a parentheses. If it's inclusive, the left side is 2, goes to infinity, but because we're including 2, we use a square bracket. Whenever we're working with infinity, we always use just a regular parentheses because we can't define infinity. If you think of a really big number, I could always just add 1 to it. So because we can't technically include infinity, we just use a parentheses. So let's talk a little bit more about interval notation. And then we'll talk about how to solve some of these inequalities. So I'll show you if we write it in set notation. I'll show you what it looks like in interval notation, and then I'll show you what the actual graph looks like. So in set notation, if we had a set of x's such that x is greater than or equal to a number a, the graph would look like this. And the way that we would write that in interval notation is on the left side we have a, right side we have infinity. We never include infinity, but because we're being inclusive, we're going to include a. Next, we're going to talk about all x's such that x is greater than a. Actually should have included an x over here, so x is greater than or equal to a here. Now, as far as what that graph looks like, we know that we'll find a, put an open circle, and go to the right. The left side would be a, the right side is infinity. So if we're not going to include a, we put a parentheses there. Let's talk about going the opposite way. So what if we said all x values such that x is less than or equal to b? Well, on the graph, you would have b, and all numbers including and less than that look like it's this way. The left side would be infinity. The right side would be b. We are including b, but infinity is an abstract concept, so we don't include that. Let's show you what happens if all x values such that x is just less than b exclusively. So on a number line, we would go to b, open circle this way. So we have b on the right, infinity on the left. We're not including either of those. What about if we had a compound inequality, where it was the set of numbers x such that x is between a and b inclusively? Well, on a number line, here's a, here's b. If we're going to include those numbers, it would look like this. If we didn't include those numbers, if we just had all x values such that x is between a and b exclusively, then we always look at the left, the right. We're not including anything, so we use open parentheses. What if we said x was the set of numbers such that x is any type of real number? This symbol right here just means element of. And in this case, that just means x is a real number. So how do we graph x as any real number? Well, on a number line, that would just cover every single number on a number line, right? So the left side is infinity, the right side is infinity, and we can't include infinity, so that's how you would write that. The last type of compound inequality I want to talk about is if we're looking at the set of x such that x is less than a or x is greater than or equal to b. So it looks like they're separate, right? So we have a, we're not including that. We have b, we are including that. And we have to join two actual inequalities. So let's start with the a one. The left side's negative infinity. Actually, anytime you're on the left side, that's negative numbers, so those would be negative infinity. I should have included that here, just simple oversight. The left side of a graph would be negative infinity, the right side of the graph is infinity. So in this case, any number to the left would be negative infinity. We go up to a, but not including a. The second inequality was b. We are going to include b, but then we go to infinity. So we're going to join those together. This symbol just means union. So that just means we're combining two separate graphs. So let's take a look at some inequalities that we'll solve. What if we had 4 minus 3x is less than or equal to 7 plus 2x? Just like a regular equation, we'll get the variables on one side. We'll get the constants on the other side. But we have to divide by a negative, so just make sure you remember anytime you divide by a negative, you switch the inequality. And that would be the answer. And if we were going to write it in interval notation, the graph would look something like this, right on negative 3/5. So you should be able to write this negative 3/5. We're including that up to infinity, which we are not. That would be the preferred answer. What if we had a compound inequality? Like negative 2 is less than 5 plus 3x is less than 20. Now there's actually two different ways we could do this. One way we could do this is, you're probably familiar with this way, is we could do everything to all sides. So let's get this x by itself by subtracting 5 from that side, this side, and this side. And then we could divide 3 here, here, and here. We get negative 7/3 is less than x, which is less than 15/3. Now, in interval notation, this would be negative 7/3 on the left, and on the right would be 15/3. The second way you could do a problem like this is to actually separate it, where this would be one inequality, and this would be the second inequality. So let's take a look. Negative 2 is less than 5 plus 3x, and the second inequality would be 5 plus 3x is less than 20. You don't want to cut this down the middle. That's not correct. The whole middle goes with the left and it goes with the right. Remember, when we are combining inequalities, we use a union. So let's solve this and see if we get the same answer. So we get negative 7 is less than 3x. We divide by 3. We get x would be greater than negative 7/3. We're going to combine that with 3x is less than 15. X is less than 15/3. So if we were going to take a look at this, right, remember that we have x's, so we have negative 7/3, and we have 15/3. All numbers that are less than 15/3 go over here. All numbers that are greater than negative 7/3 would go over here. But the way this inequality is written, this is an and inequality. By and inequality, that means that we're actually looking for numbers in between. An or inequality would look like something like this. With or, we're actually saying that the answer is this piece plus this piece, and we use a union to represent that. If it's an and problem, we actually use an intersection of two inequalities. What that means is we're looking to see where is there overlap between numbers that are greater than negative 7/3 and numbers that are less than 15/3. So the overlap would be between negative 7/3 and 15/3. So it's important that you know that. If it's ands, we're generally looking for an intersection where both inequalities are satisfied. We'll talk more about this when we get to absolute value. If it's or, we're just looking to combine all the possible solutions. And you can see we got the same answer. So let's move down to the third example. What if we had x squared minus x minus 12 is less than 0? Okay, so for a problem like this, let me just see, put something here. This is a quadratic. It's almost like an equation, but it's an inequality. So let's actually just solve this like a regular quadratic equation. What we could do first is factor. And we get x minus 4 is equal to 0, x is equal to 4, and we get x plus 3 is equal to 0, so x is negative 3. But because this is an inequality, there's an extra step we have to do. So the first step was we solve like an equation. The actual second step we're going to do is we're going to make a number line with negative 3 and 4 on it, and we're going to test numbers in each of those regions. So for example, this region right here would be any number less than 4 and greater than negative 3. This region would be any number greater than 4, and this area would be any number less than negative 3. So let's write that for step 2. Let's say test regions on a number line. Okay, so let's go ahead and pick a number in each region so we can go ahead and test it. Like I'm going to test maybe when x is negative 4. That's a number less than negative 3. Or I could test 0 here, or I could test 5 here. What I'm going to do is plug them in and see if it satisfies my inequality. All right, so on my calculator, I'm going to type in -4 for all the x's, use parentheses. So it's going to look like this: -4 to the second minus -4 minus 12. And I want to see, is that less than 0? And I'm going to do that for 0, and then I'm going to do it with 5. So let's go ahead. I'm going to try it out here. Okay, so if I use -4, my calculator is telling me I got 8 is less than 0. Well, that's not true. So that means that whole area where -4 is no good. Let's try 0. If I store 0 in for all the x's, if I type 0 squared minus 0 minus 12, I get -12 is less than 0. That looks like that makes sense. And then if I'm going to plug in 5 for all the x's, I get 8 is less than 0, and that's not true. So it looks like the region on our number line that worked was this region right here. So this brings us to our next step. We're going to test the boundary numbers on our number line. Pretty much what this means is we're looking to say, do you include them or do you not include them? So for step number 3, we know that the region that gives us answers is between -3 and 4. The question is, could x be -3? Well, I'm going to plug that in and see what we get. Could x be 4? Again, I'll plug it in and see what we get. Well, if you do plug those in, because those are x-intercepts, you would get 0 is less than 0, and that's not true. Same thing with this. So I'm not going to include them, which means our answer for this would just be this, or in interval notation, we would write -3 to 4. Let's try another one. So this will be problem number 4. It's another quadratic. So we have 2x squared plus 5x minus 12 is greater than or equal to 0. First thing we'll do is we'll factor this. So this one's a little bit more complicated, so I'll use my AC method. -24 and 5. Factors of 24 that add up to 5. Let's figure them out. I know 2 and 12, that's not going to give us 5. What else goes into 24? 24 and we have 4 and 6. No. 3 and 8. 3 and 8 would work, right? So if we have to get -24 and +5, I would use +5 and +8 and -3. So this would give us 2x squared plus 8x minus 3x minus 12 is greater than or equal to 0. Okay, well, let's factor it quickly here, and then we'll go to our next step. Get x plus 4, take out a -3, get x plus 4. So we'll get x plus 4 times 2x minus 3. It's greater than or equal to 0. This would give us -4, and we get 2x minus 3 equals 0. If you bring the 3 over and divide by 2, you get 3/2. Our next step is our number line with -4 and 3/2. Just make sure you put the lesser number on the left side, of course, and we'll pick numbers in each of these regions. So I'll use like -5 here, I'll use 0, and I'll use 2. 3.5 is 1.5. So I'm going to plug these numbers into our inequality and see if any of them make sense. Just give me a second. I'll get the calculator ready to go. And let's see here. I'm going to do -5. I'm going to plug it in for all the x's. And we get 13 is greater than or equal to 0. So that region's going to work. All numbers less than -4. How about 0? We get -12 is greater than or equal to 0. No, that's no good. And then we'll try 2 in for all the x's. And if you were to plug 2 in, you get 6 is greater than or equal to 0. That is true. So it looks like the regions that we have right now are any number less than -4 in union with any number greater than 3/2. And remember, this is a union problem because this is a number line, and right now this is what we're looking at for our answers. But could x be -4? Could x be 3/2? Well, if you plug those into our original equation, you would get 0 because those were x-intercepts. So you would get 0 is greater than or equal to 0, which is true. So those answers would be included. The way we would write this in interval notation would be, if it helps you, you could even graph it. -4, 3/2. We would have any number, so -infinity up to -4. We are including that in union with the graph of 3/2 to +infinity. So let's finish up with a different type of inequality. It's a rational inequality. This is always a popular one on your final exam and on exams in general. It looks like this. We have 5 over x plus 4 is greater than or equal to 1. All right, looks pretty easy enough. Generally, there's two ways to solve this. And we'll solve it like an equation for our first step. So we could make it into a proportion and just cross multiply. That's one way to do it. You'll get the same answer as if you were to multiply by your LCD. The LCD in this case is x plus 4. So no matter which way you do it, you'll get the same answer, as long as you make sure you distribute the LCD to each fraction. So what I'm actually going to do is I'm just going to cross multiply. I'm going to do x plus 4 times 1 and set that equal to 1 times 5. And I get x plus 4 is equal to 5, x would equal 1. All right, so step number 1 is done. We solved it like an equation. Step number 2 is you want to figure out, find the x values that make the denominator equal to 0. So look at your denominators. Well, 1 is fine the way it is, but we do have an x plus 4. So for step number 2, what we're going to do is set that equal to 0 and say x is equal to -4. Now those aren't the actual answers yet. We're not there. But let's go to step 3. Step 3 is we make our number line and we test regions. So on our number line, we're going to have -4 and 1. And just like in the last few problems, we'll test numbers less than -4, like maybe -5, 0, and 2. And we'll plug them in and see which ones work. Now, if we were to plug in -5, we would get 5 over -1 is greater than or equal to 1. That's not true. If we were to plug 0 in, we'd get 1.25 is greater than or equal to 1. Of course, that works. And if we were to plug in 2, we'd get 5 over 6 is greater than or equal to 1. I don't think so. So it looks like from our third step, we get the region between -4 and +1. So you could probably guess our last step. We just want to test the boundaries. Could x equal -4? Could x equal 1? Well, let's plug them in, or we could even take a look. What happens if we plug in -4? We get a denominator equal to 0, right? So this would actually be undefined. So the answer is no, it can't be -4. If we were to plug in 1, well, if we did the math right, we'd have 5 over 5 or 1. So is 1 greater than or equal to 1? Yeah. So we can include that value. The way that we would write this in interval notation is you think about the left side, think about the right side, and then make sure your parentheses are correct. We'll do one more problem like this. What number was this? This is number 5, so we'll go to number 6. Problem number 6, it says 2x minus 1 over 3x plus 4 is less than 5. We'll go through our steps. Let's make it a proportion, cross multiply. So we'll have 1 times 2x minus 1 is equal to 5 times 3x plus 4. And we'll get 2x minus 1 is equal to 15x plus 20. We'll bring the 15 over, bring the 1 over, and we'll get x is equal to 21 over negative 13. That looks kind of ugly. Let me just make sure I did all my math correct. So 5 times 3x plus 4 is equal to 1 times 2x minus 1. Yeah. 2x minus 1, 15x plus 20. Everything looks good. Subtract 20 over, or add the 1 over, that's 21. Subtract the 15, that's negative 13. So that looks right. Our next step is we want to make our denominators equal to 0. So that would be 3x plus 4 is equal to 0. If we bring the 4 over, we get x is equal to negative 4/3. So we're going to make our number line with these numbers. Now, 21 over 13 is about 1.6. Negative 4/3 is about negative 1.3. So let's try to pick numbers that allow us to get an answer here. So negative 1.6 is smaller, and negative 4/3 is a little bit bigger. So if we were to pick a number less than negative 1.6, we could use negative 2. Between negative 1.6 and negative 1.3, let's use negative 1.4. And then greater than negative 4/3, we could just use 0. So what I'm going to do is I'm going to plug them into 2x minus 1 over 3x plus 4 is see if that answer is less than 5. Now I want to show you a little bit of a trick here. What I'm going to do is I'm going to actually use my calculator's advanced storing technique to plug in these numbers a little bit more efficiently. You don't have to do it this way. You could plug them in manually. But on Blackboard, I recommended that everyone get a TI-30X2S. And in the bottom left-hand corner, it says store. S-T-O with an arrow. That means the calculator is going to remember a number. It's almost like programming. Now, if you want to store a number, like we want to start off with negative 2, I'm going to type negative 2. I'm going to hit the store button, and I'm going to go to A and hit enter. What this is telling your calculator to do is every time you push A on your calculator, it's going to plug in negative 2. So negative 2, store for A, hit enter, and my calculator says, all right, ready to go. Next thing I want to do is program my calculator to figure out this value. So in order to get A on your calculator, the way that we do it is we actually hit the button above it. It says memvar. We're going to go over to A and then hit enter. So on my calculator, this is what I'm going to type in. I'm going to type 2A minus 1 divided by 3A plus 4. And it's a little bit easier because you don't have to worry about parentheses. So my calculator is already stored. So I'm going to type 2 mem variable A minus 1 divided by parentheses 3 mem variable A plus 4. And my calculator is saying 2.5. Well, is that less than 5? Yeah. Now all we have to do, we don't have to type in all this stuff all over again if you do the store technique. Just type negative 1.4, hit the store button, hit enter on A, and hit the actual up arrow. Go back into the equation you typed in and hit enter. I'm getting 19. Is 19 less than 5? No. And then we'll type 0 store for A, Let's see what that is. I'm getting -1/4. Is that less than 5? Yeah. So we're almost done here. It looks like the numbers that work would be numbers that are less than -21/3, 13ths anyway, sorry, in union with numbers that are greater than -4/3. And we just have to test the boundaries to see if we are going to include those or not. So if I store a -21/3 for A, go back, my calculator is telling me I get, let's see, -21/13. Did I type that incorrectly? My calculator is telling me 5 is less than 5. Well, that's not true. It's equal to, but that's not what we're looking for. And how about -4/3? Store for A. And my calculator is telling me domain error because that number makes our denominator 0. So we're not going to include any of those. On the number line, you could see then that in interval notation will do from -∞ to -21/13 in union with -4/3 to infinity.